In this video, we're solving a kinematics problem where the acceleration is not constant. And that means all those standard formulas for constant acceleration in one dimension are invalid. We have to go back to first principles here. So we're told we have an acceleration function that's linearly decreasing. It's given by 2 minus 0.1 t, where all these units in here are just guaranteeing that the units on each term come out to meters per second squared. So notice in the second one, that's a negative 0.1 meters per second cubed times t, because t carries units of seconds, and one of those will cancel, giving us meters per second squared. So when we start actually working with this acceleration function, I'm not going to write those units in every step. They're just too distracting. So what I mean by first principles in this problem is we go back to the derivative relationships between all the kinematic variables. So our first kinematic variable is position. So I can talk about position as a function of time, and then I can talk about velocity. And velocity, remember, is just the time derivative of position, so x prime of t. And then I can talk about another time derivative. That's the acceleration. So the acceleration is the rate of change in the velocity function, so v prime of t, which we could also write as x double prime of t. So those are the first principles. And then what we're asked to do in this problem is actually find the equations of motion for the car. That's velocity as a function of time, and then position as a function of time. And we need to make a note of the initial conditions here. This car starts from rest at the origin. So the initial velocity is 0 and the initial position is 0. So to get these equations of motion, what we're doing is completely analogous to the derivation of our 1D constant acceleration kinematics equations. It's just now we have a non-constant acceleration. So the starting point is to say our acceleration is 2 minus 0.1 t. And then we go, okay, well, I should be able to get to the velocity function because the velocity is the thing I differentiate to get acceleration. In other words, the velocity function is the antiderivative of the acceleration function. So we just guessed the antiderivative, that's 2t, and then minus 0.1 times a 1/2 t squared, just using the power rule there for antiderivatives. And the antiderivative comes with the flexibility of an arbitrary constant because the derivative of a constant is 0. So we're left with a little question there. What's the c going to be for this velocity function? And that's where the initial conditions come in. The car starts from rest, meaning v of 0 must be equal to 0. So we're plugging in an initial condition here. V equals 0 at t equals 0. So let's see what that implies. Replacing v with a 0 on the left-hand side, I get 0. Replacing t with 0 in both of these terms, those are both zeros. And we're just left with a c on the right-hand side. Well, it looks like c turns out to be 0. This allows us to nail down what's called the particular solution for our velocity function. So I end up with v of t is equal to 2t, and I'm going to clean this up. 0.1 times a half, that's 0.05. So I have 2t minus 0.05 t squared, and then it turned out the arbitrary constant c was 0. So next we're looking for the position function, and we know the derivative of position gives us velocity. In other words, we just need to guess the thing we differentiate to get this expression for v of t. So x, or x of t, is the antiderivative of this expression. So the antiderivative of 2t is just t squared. And then I apply the power rule again to this quadratic term, which gives me a 1/3 t cubed. So I have minus 0.05 over 3 t cubed. And then again, the flexibility of an additive constant that we'll call c. So now we apply initial conditions again. We're told this car started at the origin. So the initial position is 0, x equals 0 at t equals 0. And I'll write this a little more compactly this time because I'm running out of space. If I replace x with 0 over here and t with 0 on the right-hand side, because that was my initial condition, everything there is 0 except for the c, so the c must be 0 as well. So finally, we can write down the position as a function of time, and I'll go ahead and use decimal approximations for the 0.05 over 3 part, and I end up with a t squared minus, keeping 3 significant digits here, 0.0167 t cubed. So now we have the equations of motion for this car telling us the position and velocity as a function of time, and we're done. If you enjoyed this video or at least found it useful, Check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.